What's up guys, welcome to the series about design patterns and how to implement them on AWS using only serverless services. Our first one is the Strangler pattern, and this is how it looks like. Say you have a legacy application or even a modern solution that is running as a monolith with a load balancer in front of it. And you see the /* here, meaning that all the traffic is being routed to your current legacy application. But now you decide it is time to break away from that monolith and it is time to decompose it into a bunch of microservices and applications, but in a phased approach. So you pick one domain of the application, you pick the user's domain, and you migrate it into a serverless microservice or a set of microservices. So using Lambda functions, you see that I created a Lambda that adds a user, another Lambda that deletes a user. And you could continue building all the services that your domain has. And with the help of the application load balancer, you will route all the traffic, all the requests that starts with /user. Now you're able to route them to your user's microservice. I also added, for the sake of the example, a couple of DynamoDB tables here. Probably you'll be using just one, just to illustrate how this part of the application can be talking to its own data store. And now the data is decoupled as well. Okay, but what happens if the legacy application, your existing application, requires that data? After all user calls are now being processed by a whole different application, the user's one, and being stored in a whole different data store. Well, we can leverage something like DynamoDB streams. So effectively, every operation on the database will trigger a Lambda function that syncs that data back into the legacy application. So instead of a big bang approach completely replacing a complex system with microservices, the Strangler pattern, as you can see, allows you to proceed decoupling your domains gradually and migrate them into a new system, which reduces the risk of a complete failure. From the client's perspective, nothing changed. The routing facade takes care of pointing to the new location. And thanks to DynamoDB Streams feature, your data is synchronized back to the legacy application, so the existing functions that have not been decoupled yet can continue to operate normally. By the way, the name Strangler pattern was inspired from Strangler fig trees. So we just talked about a use case where this pattern is best used when you're looking to migrate from on-prem to cloud, or if you're already done a lift and shift workload and you're looking to re-architect it to be more cloud native. But that might not be what you hear in a conversation with your manager or with your colleagues. Maybe they will say something along the lines of, currently we're operating a monolithic application and I don't see any room for serverless. So that's the indication you should consider looking at the Strangler pattern, which will introduce two benefits. Well, first, you'll start deconstructing the monolith into a microservices architecture. You'll start advancing, gradually migrating, testing, and deploying all your domains until eventually all the old legacy systems features are phased out. Now, the benefits of adopting serverless services like Lambda functions and DynamoDB for this pattern is the ability to focus on functionality without worrying much about the ops aspect, like servers provisioning, maintenance, relying on sysadmins or cloud engineers to orchestrate all these infrastructure changes in all the environments, right? And secondly, it will allow your team to slowly start adopting more cloud native services that come with the scale, the resiliency, and all the other benefits that AWS Cloud provides. So what should you consider before kicking off such a migration? Well, first of all, this pattern cannot be used in systems where requests to the backend cannot be intercepted and routed, right? We rely on the API gateway here as a facade to do the routing for us. And not all apps are built this way. So just something to keep in mind. And also the fact that oftentimes legacy systems are not designed to provide the same level of responsiveness and resilience that you see in serverless, which brings us to our next pattern. Second one is the circuit breaker pattern, which is a pattern that you typically use for calling any external or any internal API for that matter. And I'll go through the diagram, in the next slide. But say you have a application that requires payment processing, and you're using Stripe or PayPal as your payment processor. Now, these third-party solutions will most likely throttle or rate limit your calls, right? They won't just open the floodgates for you. So you want to avoid exhausting your own resources in case of an error, an infinite loop, a DDoS attack, or whatever issue that may cause a malicious burst in load. So the circuit breaker is exactly what you would have envisioned if you had no idea about this design pattern. It's like a circuit breaker in your house. If the voltage spikes, it will click and it will save the whole circuitry from catching a fire. By including the circuit breaker pattern in your design, especially when done with serverless, it allows you to improve your cost efficiency right out of the bat. One of the core tenets of serverless is you pay for usage. So if you manage to avoid making any unnecessary calls, that automatically translates into savings. And the first thing you should consider is the addition of dead letter queues, DLQs, mainly when you want to retain something for future retries, analysis, inspection, at a later date. And the second thing is this pattern is only suitable for synchronous requests, and you'll see why on the next slide. So let's look at how we can implement the circuit breaker pattern on AWS using nothing but serverless technologies. Requests can be coming from an external source, like your front end is sending requests through an API gateway, or they can be made internally. But the important thing is you're invoking a microservice, a Lambda function in our case, which is calling an external service, right? So the Lambda keeps track of the error counts. So if the external service fails, say you're calling a PayPal API and it fails, well, let's say, your Lambda will try at least 3 or 4 times, depending on your use case, right? But at the same time, you don't want to keep trying forever. So after those 3 or 4 tries, you want to log the error events. And EventBridge is a perfect tool for this kind of behavior, because once you capture that error event and send it to EventBridge, well, EventBridge can then invoke another Lambda, which can now create an entry in a DynamoDB table with a TTL set of, 60 seconds, 2 minutes, or whatever you want. So now you just want your Lambda function, the one calling the external service, to read from the table, check if there's an entry. If there's none, then Lambda is gonna try. But if there's an entry present there saying that there's something wrong with the external service, well, the Lambda function can just break the circuit right there, right then, and respond back to the API gateway, which will respond back to the client. All right, so we'll look at pattern number 3, the router pattern. Your use case is asynchronous invocations, right? And I'll give you an example I had recently with a customer where they wanted to implement a data lake with serverless stack. So one of the decisions they had to make is if someone drops a file in an S3 bucket, they needed to process that file. Now, the challenge is there could be different types of files, right? Someone could drop a CSV file, another person could drop a JSON file or a Parquet format, and they had to have a different logic of processing that data and then store it in their data warehouse. So we ended up building a Lambda function that just looks at the file being dropped, gets the extension, reads a few lines to build up the schema, and then it submits it into the right queue where another Lambda function is waiting downstream to process it. So all my Lambda function was doing is routing requests to the right Lambda function based on the parameters I mentioned before. Benefits. Again, decoupling. as we continue to look at these patterns in order to build a resilient, event-driven architecture. And at the same time, using serverless makes it extremely cost-efficient and very simple to implement. You can think of this pattern as a glorified switch statement in your Lambda function, right? Again, keep in mind, this is not a server bullet. It gives you limited error handling and parallelism, because if the downstream Lambda fails, and we'll see that in the next slide, there is no directly handling of these edge cases, right? And that's because of the asynchronous nature. And of course, if your requirement is complex decision making, then it's preferable to use something like state machines, which we'll not be covering in this specific video, but I will be covering in the next one. So make sure to subscribe so you won't miss it. And you'll see why this is for a simpler solutions looking at the architecture diagram. You have requests coming in, let's say from an S3 bucket, given the previous example. The S3 bucket triggers the routing Lambda. And it's this Lambda that decides what to do based on the type of the file. Your dynamic router knows this will be a service A job, so it invokes the Lambda A. If it's a service B job, then it will invoke the Lambda responsible for service B execution, and so forth. So the dynamic router now is only making decisions on where you need to send the request next. That's all its job. It will not sit there waiting for service A to finish doing whatever it needs to do and then return something, right? This is again a very simpler architecture. And the dead letter queues, DLQs, are something you should always consider if you're running an asynchronous workload. In our example, the dynamic router Lambda is invoking other Lambdas downstream. But if one of these downstream Lambdas fail, you want to have the ability to investigate and have an analysis performed, right? You want to understand what happened. You want to understand what kind of patterns that are causing this specific failure. So the pattern we'll look at next is the distributed trigger, commonly known as the pub sub, where basically you have a publisher and a subscriber. This is a messaging pattern where the publisher doesn't know about where the subscriber is or how are they going to use the payload, so there's no direct correlation. So if your colleagues, products people, your lead is voicing out the need of asynchronous and parallel execution, and we'll take a look at the diagram right after this, well, this might just be the right path to explore. Because in its core, this pattern allows your architecture to fan out into a whole plethora of services. And I want to mention that this is different from your queuing-based messaging. Queuing is used to buffer the messages, right? Buffer the incoming requests. It's actually our next pattern. This is more about fanning out the incoming requests from a publisher and delivering the same message to multiple services downstream, because each service is going to consume this message and do something entirely different with it. The benefits you'll get is, well, now you're having a loosely coupled architecture. So instead of having the publisher and subscriber tightly coupled with each other, you introduce a messaging bus in the middle where the publisher is just going to dispatch a message into the bus, and the bus is smart enough to know where the subscribers are and make sure they'll get those messages. And it could scale well, right? And this is the whole reason why we're using a pure serverless stack. The other benefit about fanning out is, well, the ability to fan out to multiple subscribers of different types, which is the key to understanding when to use this specific pattern. So if you're discussing a case where you have a message coming on and you have, say, 5 different microservices that needs to consume that same message, but do different things with it, well, this is where you should channel your thoughts towards trying to fan out the architecture and use this pattern. Some considerations are that you should think about your use case and you should ask yourself a few questions. Is message duplications important? Is the ordering of the messages important? Am I going to have to be sharding my data? What is my data retention policy? What is the message payload size? Is it 64 kilobytes? Is it 1 megabyte? Is it more than 1 megabyte? And knowing this will give you all these discussion and brainstorming points, because I don't want anyone watching this and thinking that these are the patterns and I will just paste them into my architecture and they will just work. it doesn't work this way. These services are built for specific needs, right? You could look at Kinesis and compare it to SNS and even Bridge even, and they all operate sort of the same. They're the same, but they're different, right? So are you looking for ordering? If so, go with Kinesis. It's your best bet. Are you looking for large message size that you want to dispatch? Well, again, Kinesis is your best bet. But does your use case require a huge number of subscribers, up to 10 millions? Then SNS is your best bet. Or are you doing some sort of event-based filtering? Then Even Bridge is your best bet. So again, understand the needs of your application, then implement the right service. The pattern will still remain the same, right? It's just the way you will implement it and the services that you will use that's going to differ. So you have your requests coming in through API gateway, and the API gateway here just exposing an endpoint that says create user. And then all it does is forwarding that request directly into an SNS topic. So the publisher in this case is the API gateway. And as you can see, the SNS topic is now connected to several subscribers and it's delivering to them the same message payload. So you could have a Lambda that looks at that message payload and updates a data store. That's all that microservice does. You could also have a Lambda that looks at the same message payload and its job is to set up a profile for the user. The third one looks at the same message payload and sends a welcome email, and so forth. You get the idea. So during your architecture review, if you find yourself dealing with a use case where one action triggers several actions down the road that can be run separately and in parallel, then that's where the PubSub patterns comes a long way. And you see how it can all be done using the serverless stack. You literally don't have to worry about scaling, patching resources, or managing servers fleets. I want to mention again that SNS is not the only way you can do PubSub. For example, you can use Event Bridge if you have a use case where you need to perform some kind of event-based filtering, right? If this event happened, call Lambda A. If this other event happened, call Lambda B. Or you can use Kinesis if ordering is super important for your use case, because SNS will not guarantee orders. But the pattern will still be the same, only the implementation and the services choice will differ according to your needs and constraints. And we reached our fifth and last pattern for this episode, the decoupled invocation or the queue-based load leveling. I talked about a few messaging patterns already, and we took a look at the PubSub where we leverage SNS but we can also use Kinesis, or we can also use Event Bridge to do the same thing. But those services are not exactly the same as SQS, right? I mean, both of them are messaging patterns, but the use cases are different. So I included this pattern just to show you how we can use SQS with a different use case. You're using an API gateway, which is super scalable. It's able to handle a ton of requests, but the downstream application is not able to process all the incoming requests. And I see this a lot with customers. Your downstream application needs a buffer of some sort. You basically want to queue these requests coming in order to be able to add resiliency to the architecture. Another use case might be that your API needs to perform some kind of expensive computation that's taking a lot of time. And we know that API Gateway has 29 seconds timeout. So how do you implement such a thing? And it depends on your requirements. You can brainstorm with your team and ask the question, do you really need a response? Right? Maybe instead of waiting for a response and hitting that 29 seconds timeout, maybe your call can be asynchronous and you only have to get the 200 acknowledgements. Or you can ask, can we do something like a webhook pattern where the client knows the job has been accepted and being processed, and then it offers another endpoint that the client can continue to pull frequently and check if the job has been finished. Let me know in the comments if you want me to cover the webhook pattern. I might add it to the next episode. Introducing a serverless queue between the services can act as a buffer buffer, and it can alleviate a lot of concerns, right? So we go back to our first example. Your front end is super fast, your back end is not quite there yet, which is the classic fast producer, slow consumer problem. And you want to make sure your application can sustain the load that is coming in by buffering all these requests and not losing them. And it also gives the benefit to the downstream consumers to process the incoming requests at their own pace. So what should we keep in mind? Well, if you're looking for a synchronous response, again, this is probably not the right solution. We're decoupling our components, so the whole architecture becomes asynchronous, right? But you can use that to your advantage, as I mentioned before. So we're not only decoupling the monolithic design here, but we're embracing asynchronous style as well. The other consideration is the concurrency limits that we need to use to our advantage by being mindful of the execution time. You know that accounts have limits. It is a soft limit, but it's a limit nonetheless. We don't want to consume all the resources in the account. As we say, the cloud is not infinite, even if it might seem like it. So your design should always include a cap. Because, and we'll talk about it in the next slide, you never know if the next spike in traffic is a DDoS attack, right? You never know when you have this burst, you never know whether it's malicious or not. So you don't want your workers to be spinning left and right and center, trying to support those malicious requests. So having a capacity limit restriction on your Lambdas also helps in terms of ensuring the resiliency in your architecture. So let's build our example together. You have your API gateway handling incoming requests from clients, right? Well, we'll say we have hundreds of thousands of requests coming in, but you see that now they are being interjected by SQS. They are being stored in the SQS buffer. On the other side, you include a Lambda worker, which can now do a batch processing of, say, 10 requests at a time. So you're using the Lambda concurrency model to your advantage by setting a concurrency limit. But you also are accepting those messages in a batch manner, so you can scale up and you can scale down based on your needs. And because it's asynchronous invocation, DLQ should always be part of your design, as we learned by now. Or you can also take a look at Lambda destinations. It is a pretty sweet feature where you can route messages based on particular patterns, and you can do interesting things with that. So as you see now, you are throttling, you are kind of chewing up those thousands and thousands of requests into an elastic, scalable SQS buffer. And then you have a Lambda that can scale and can do batch processing to make sure that you can keep up with any traffic spikes you might encounter. And there you have it, ladies and gentlemen, for this episode. I really hope you enjoyed this content. If you did, don't forget to give the video a like. This actually tells me it was beneficial for you and I should make more similar videos. So until then, be safe and see you soon.